My name is Jose Martin-Garcia. I work on several projects at Wolfram, one of them being the Geo project. So as in previous conferences, I'm going to be presenting the more computational aspects of the additions this year for Geo. So the main thing for us this year, or one of the main things, is the change from having GeoGraphics backgrounds being mostly based on images to GeoGraphics backgrounds that are vector-based. So this means that this year we will be reviewing vector geoprimitives. We will see a new object we have added called GeoPolygon, a function GeoBoundary to compute boundaries of 2D geoprimitives. And then I will focus on two aspects that are particularly demanding of computation regarding vector geographics. I should say that in the next talk, Francisco will be will continue talking about vector geographics. And this year, the separation between computation and data was particularly difficult. So to make both talks self-contained, there will be some overlapping in the topics we discuss. Okay, so let's go with the first part. Well, here I have a map similar to the one that Steven showed yesterday. And this is a map of around the area of the Eiffel Tower. He was showing yesterday the area around Notre Dame with the same style. Here, as I was saying, everything is vectorial. Every building is a polygon, every street is a line. We have labels, text, objects, etc. Everything is vectorial here. And so these will allow us to be a lot more powerful in the specification of styles, and also the images, of course, will be, or the results will be crispier, and now you will be able to enlarge the maps as much as you want. So regarding primitives, I want to start by having this table in which we see the various primitives that we support in the Geo project. Until now, we have used this combination of flat primitives with geoposition information inside. We will continue using that, of course. And but I would like to focus today on the more geo-defined primitives, those that are defined on the surface of the Earth and have a very definite geometrical meaning. So in 0 dimensions, we had the marker already. And in this table, we see the column with 2D primitives, the column with 1D primitives, and the relation between the left column and the right column is just boundary. So we will be adding these two objects just to complete the table, you see? And so the boundary of a geopolygon will be a geopath, the boundary of a geodisk is a geocircle, geohemisphere has its own primitives for the boundary, geovisible region, the same thing. GeoBounds region, we add this one again to complete the table. And then we have these two special cases of geohemisphere, depending on time, with boundary day-night terminator. So I want to start by reminding you of the geometric meanings of these objects. So geodisk and geocircle are the simplest ones. So we have here a geocircle centered around Rome with 3,000 miles of radius, and the boundary is this one. So the definition of these objects is that they are formed by radiuses that are geodesics themselves. So this is clearer if we select just a range of initial angles, right? So in this case, we see how we have this object formed by all these radiuses. So I've selected just in terms of 15 degrees. And this is the corresponding geocircle. So now, for example, if we compute the geoboundary, this is the new function of a geodisk, we get, of course, the geocircle with the same center, the same radius. Now, if we have a geodisk that has only a finite, or well, not complete range of angles, then you see that we get these more complicated objects. The reason for that is that now, of course, we need to give only also these two lines, these two geodesics, as part of the boundary. So this is what this is doing, it's joining this segment and the two geodesics. Okay, so geovisible region and its boundary, I think I haven't explained here in detail what these do. So what we take, of course, this is an Earth which is highly exaggerated in eccentricity. So what we do is that we take a point over the surface, could put it farther away, and we see how the visible region changes. What we are doing here is just tracing lines, and so the point in which the lines from this point are tangent to the ellipsoid are those that define this visibility region here, right? So that's the thing. And the interesting thing is that these, we are moving the point along this line, this red line, and there is a transformation from this angle to that other angle, and this is the vector which is always perpendicular to this line. This line happens to be an ellipse, and it's on a flat plane. So what we are doing is just cutting the Earth with a plane, and just where to put that plane depends on the position of that point. It's very simple. So if we take, for example, that point at an elevation of 400 kilometers, we can compute, well, we can describe this as the visibility region. The geoboundary would be, as we were saying, the geovisible region boundary of that same point. And now we can just draw the 2D region and the 1D boundary. And we are doing this with one of the new vector styles. The geohemisphere is a particular case of visibility from infinite length. So now we have exactly the same diagram, but now the point is infinitely far from the center of the Earth, and the plane with which we are cutting the Earth happens to go through the center of the Earth. And so the lines that are parallel to the red arrow will be tangent to that point and that point. And the same thing happens. So we have now geoboundary computing the boundary of the hemisphere. Here we have a hemisphere and its boundary. And there is a particular case in which we put a date here or an instant, and this is able to give us the hemisphere that this is the night hemisphere. So we are in this part, daylight, and this is the boundary between the night hemisphere and the day hemisphere. That's very simple too. This one is defined as, this is a new object, which we have added for completeness. And this is just a rectangle in latitudes and longitudes. It's very simple. And so we have that object, that's the GeoBounds region of the US. So it's bounding in latitudes and longitude, the US, and this is its boundary. So yeah, and this is another of the styles. Francisco will explain in the next talk these various styles we have now. Okay, so let me introduce the new object, GeoPolygon. So GeoPolygon corresponds to the 2D region of GeoPath, and it has several interesting properties that I want to discuss today. So let's take some latitude and longitude points. So we have these 4 points, right? So we put them in this object, GeoPolygon. Now, if we do a GeoGraphics of this object, we get that. What we see here is that it's automatically computing the geodesics. So meridians are geodesics, but parallels are not. So this point and that point are not joined by a straight line. They are joined by that geodesic. Same thing happens on the south hemisphere. So what's the boundary of that GeoPolygon? Of course, it's a geopath, which by default also uses geodesic segments. So we can draw it, and we draw it also as an arrow. So we see that we are following the points of the boundary in counterclockwise order. This will be important in a moment. Following the new polygon with holes notation, we also specify holes in the same way. So we put our boundary, our outer boundary, arrow, and then the list of holes, which in this case is just the same points divided by 2. Yes, so that's the hole, and you see how the geodesic has different curvature on the map. Okay, so what's the geoboundary of that object? The geoboundary will be now a geopath containing 2 independent segments, this one and that one. So let's see. So 2 independent geopaths. For example, these also, again following polygon, will have the multi-polygon notation. So we can have the object we had before plus this object which has been, it's the outer one shifted by 50 degrees. And so now we see these 2 objects. And you see how they are always treated independently. So if they overlap, they overlap. GeoPolygon will not stop to analyze those overlappings. The boundaries now, of course, now we have 3 lines. So this is the multi-geopath containing the 1, 2, and 3 lines of points. And notice also how the lines must have 1 point more in order to be closed. Right? So we started with 4 points, the boundaries have 5 points. Yeah, those are the boundaries. Okay, so something interesting is the following. If I'm given just one of these lines, how do I know which side of the earth do we want? So most of the systems out there for GIS, for geo work, impose the restriction that the polygons must have at most half of the earth in extent, but we don't want to do that. So GeoPolygon has now a second argument in which you can specify in various ways which side of the earth you want. So for example, we can say, I want a smaller area, and it will give that. Or I want a larger area, and then it will return that one, which is a complementary one. Or for example, remember that we were traversing the points in a counterclockwise way. So we can specify that we want the left area as we traverse the points, or the right area as we traverse the points. Another possible way of specifying which side you want is by specifying an exterior point or by specifying an interior point. This specifies the exterior point to all the lines here. This specifies the interior point for a particular outer line here. So these are the same specification. So this is the North Pole, so that point over there would be exterior. This is an interior point, which is this one. So we get the same thing. We can do the opposite. We can now say that the interior, the exterior point is 0, 0. So if this is exterior to that line, it means we want that area here. Or if you want that as interior, North Pole is now interior, then we mean that one. Okay. Another thing that we want with is that by default, GeoPolygon is adding segments, not as straight lines in the map, but as geodesics. We can specify now the possibility of choosing some other type of segment, say a loxodrome. Right? And of course, when we compute the boundary, it will inherit in the geopath which type of geopath we are using. So now we see the difference with the diagram before. So both parallels and meridians are loxodromes. So they get that. And this line is also different from that line. So you see how GeoPolygon now allows you to specify multiple things. So it's a very flexible geoprimitive, the general geoprimitive from now on in 2D. So what can we do? So here there are a few examples. Now with GeoPolygon, we can express the whole world as a single object. So this contains the same points that our current specification of the band of the world polygon has, but we are now doing it with field curves and lines and geoposition, etc. This has directly all the numbers inside with holes. For example, notice how the Caspian Sea is a hole in this other big polygon. So this has more than a quarter of a million points and more than 6,000 lines, because there are many islands. So that's something we can do now, expressing the whole world in a single object. For example, as I was saying before, if you are given the points of the equator, how do you know which side of the world you want? So, right, so we are given those points, and again, notice how we are giving them in a definite order. So we can say, give me the hemisphere in which I am, here, or the one that contains the North Pole, or give me the opposite hemisphere to where I am, or the one containing the South Pole. Another thing that can be now treated better is Antarctica. So what we always did with Antarctica is that in order, we had a line that goes from one side of the, from minus 180 degrees to plus 180 degrees longitude. And to specify which side of the world we wanted, what we were doing was to specify where to close in a rectangular map, meaning we were giving 2 points very close to the South Pole. So if we add the boundary of that GeoPolygon, what we see is this line, a very, very small circle there, and the line comes back and continues. So now I can express Antarctica just with 2 points less, which are the 2 points that were given here. So this had 1387, this has 1385. It's just the line from one side to the other side. But now, of course, we can compute the boundaries, the bounds, and it goes all the way down to minus 90 exactly. And if we plot it, the GeoBoundary doesn't have that line. So it's just this closed line. So this is the sort of topological computation that we can do now better with GeoPolygon. And finally, one more example of how to compute holes. Imagine that you are given these 2 lines, this one and that one. So how many possibilities do we have? Well, the simplest one is to say they are independent regions. I put them there and there inside GeoPolygon. So this is a multi-polygon. There are 2 completely independent regions. Now we can say that one is a hole of the other. And this is interesting. Now I can say line 1 is the outer one and line 2 is the inner one, or vice versa. Effectively, the 2 situations are identical. I'm just saying here in these 2 notations that both lines are boundaries of the same connected region. And the main difference is that in this case, this is the exterior, the canonical exterior point or a region, while here it will be here. But they both express the same situation. Or we can now say, for example, take the 2 lines and specify that this point, 0 minus 80, is exterior. So that point is exterior. So from the point of view of this line, obviously we need to get that region. And from the point of view of this other line, and because I have expressed them separately, they are independent, this is also the exterior. So I want that. Right? So this area is covered 1, this area here is covered twice. Okay, so you see how this allows expressing various situations as you may need. And finally, this was added in version 12.1, but I want to remind you of the existence of this. So this is a way of working with the regions functionality using geo objects, which is very powerful. So we take the polygon of the US, we take some projection with specific parameters, whatever. So that would be the projection we are using for the world. And what we can do is to project the primitive. We use GeoGrid position exactly as we do for geoposition, right? So we take the GeoPolygon, project it, and now these objects, the polygons that have been projected, can be handled by area and the other region functions, and they will use the coordinates that are used in the projected space. So for example, this map is able to place the US exactly as what must be in this projection using the original polygon of geogrid position. But we can take the geogrid position, directly express it as a mesh region, which of course we can use exactly as before. It gives you the same area we were obtaining before. And now we can also put that grid mesh directly on the map. Right? And as long as we are using the same projection here and the projection we used for projecting this object, which was hidden here, then it will all match. And once you have this grid mesh, you can use all the region functionality available in Wolfram Language. That's very powerful. Okay, so that was the main part of the talk. And then I want to quickly cover two algorithms that we have developed to work with vector tiles, and that are particularly demanding from the point of view of computation. So I want to show you here how the data comes from the GeoServer in tiles. And here, this is the case of Zoom 0, in which the whole world comes in a single tile. It's just that one. And we see how we get polygons, lines, which are all these borders, and points. These points are prepared for placing labels there. Francisco will explain that. And then, right, notice also how the ocean is the actual polygon. For example, all of Eurasia is just background, right? So you see how this border of the polygon enters here. America, in this case, is just a hole in the polygon, right? Like Australia, etc. Right, so this has random colors and the data comes from OpenStreetMap. So if we do the same for Zoom 2, what we get here are again lots of primitives, and you see how they come tiled. And also, very important, there is a buffer region in which the neighbor tiles overlap. So this is inconvenient for further computations. So something we want to do is to merge them, and we have to merge them very fast. So we have developed functionality that is able to take that structure, and in a very small fraction of a second, it's able to give you this other equivalent structure, in which still this is just a single polygon of the oceans, and America is still a hole in that polygon, but we have a single structure right now. And this is done at all Zoom levels. For example, this is Zoom 8 around Chicago, and you see again here the structure of tiles. This is extended throughout the whole map. You see, for example, here how these two regions match, or there, etc. So we merge them into a single structure, and that is what we see. Again, Francisco will explain later how this whole thing is then styled, and then in one of our new styles, it will look like that. Okay. We are treating those objects also as we treat our geo primitives with projections. So they come in a very particular projection, Mercator data. And so this is a function that constructs the projection we need. So, right. So here I've just taken the lines of the previous map, put them there, and you see how we can handle them or in any projection. So this will be the original. Oh, something I forgot to mention is that the data comes in integer values. So that helps a lot in merging all these polygons, because we do not have to deal with reals. Okay, but again, all these lines can be extracted from the previous map, and then you have at your disposal all the data in the tile. And very quickly, the final second algorithm that I wanted to comment is about how we place labels. So this is, again, something quite demanding because some situations have tens of thousands of labels to handle. So we need something fast. We get 3 types of labels: labels for points, for lines, for polygons. And the priority is to avoid collisions between them. So what we do is that we have developed efficient R3 algorithms, and I want to show you an example. So this is just a function to compute a number of boxes. In this case, it's just 1,000 boxes. And for example, they are those boxes. So many of them overlap. So we put them here in this function that for the moment is in a private context, but we hope to be able to expose it in the future. And you see how in a fraction of a millisecond, it selected nearly half of them. And then we have that result, right? And so we could have taken, I don't know, 100,000 boxes. Now I'm not going to plot it, it will be totally black. But the important thing is that it's still in a fraction of a second, we can select about 2,000 boxes that do not overlap. Right? And then many of the boxes come rotated. What we do, rather than having to compute overlappings with trigonometry, which would slow our R3 algorithm, what we do is that we break these labels into several boxes so that the cover doesn't extend very much the area. This is the number of boxes we are using. So the larger it is, the more boxes we need. But the important thing is that this can be done in any direction. We can also shift the center of rotation if needed, because sometimes the labels are shifted. And then these oriented boxes, which are the ones that are very efficient in R3s, are the ones inserted. And so now we can easily do that sort of thing. And my last slide is about labels of lines. So here you see, for example, the Sangamon River, how we placed it 3 times. And so what we do is that the algorithm takes the river, considers all the possibilities. Here, it ranks them. Here, opacity is the ranking. So this is beta, etc. And then it selects 3 that are far apart enough. And yeah, it could move them to one side if needed. Okay, so it's almost time. So version 12.2 has experimental support of vector geographics. This made us improve our handling of geoprimitives. And now, yeah, we have developed especially demanding computations as new algorithms that we hope to expose. Okay, and let's see if I see that Francisco and Brett has been answering questions. So actually, I don't think I have much time, but I do recommend you go now to Francisco's talk, and he will continue discussing the data and styling parts of vector geographics. Okay, I leave it here. Thank you. Bye.